Hello. Um, Welcome to another wonderful week, Comsci Club. Uh, Now, I will make a confession. This week, I was a little busy with uni apps, so the lesson may be a little less organized than usual. But we are going to be touching on kind of the third big searching algorithm, which lets you deal with weighted graphs, and that would be Dijkstra. But we're going to be going into that just later because we still have to take up a question. If you guys remember, I left you guys with with a question to do. Now, this solution that I'm going to present to you is not the most efficient one possible. There are actually quite a few ways that you could optimize it, especially regarding memory usage. But this is a very straightforward solution. And it's also a solution that I have made before. Uh, so I'm just going to use it. In Excel, right? I'm going to up the zoom a bit. So in Excel, for example, let's say at A1, I have a value of 8 or 7. And then B, I have like 2. And then after C, I have 1. Okay, so we know that you can also... so when you're putting the value of a cell, the cell's value can also depend on the value of another cell. So for example... for A2, I could say this equals A1 plus 2. So whatever value is inside A1, it'll always be 2 more than that. And then you can also depend on other things, right? So like A could depend on A2 plus A1, right? And then after you get that, and this can go on for quite some time, right? But one thing you can't do is you cannot do this. You can't make a loop. You can't say, okay, well, this is equal to D2, and well, D2 is going to be equal to C2, right? This creates a circular reference, and Excel warns you about it immediately. So you can't do that, right? And in this case, we're just going to output a star there for a value that we cannot calculate because it's circular. Okay, so that's essentially what it's asking us to do. It's placing us some restrictions so that it doesn't grow too large, because we are not Microsoft engineers here and we don't have, many years of experience under our belt. But we can implement something relatively simple here. Now, it does give us constraints. So it says that the cell can have a value of 0 or 1,000 to 1,000, or it can add up to 10 other cells. And then it says that there are 10 columns and 10 rows. So our input is essentially just the spreadsheet, right? So every column, every row, it gives you a value. The very first thing that you'll notice here is that when we draw this over here, we'll see that this kind of, the way that we're referring to, right? Like A1, B5, we can't really use that very easily in just a very simple list here. Now, of course, we get a dictionary of lists and stuff, but for simplicity's sake, we just have a 2D list. So the first thing I'm going to do is I'm going to set up a helper function that's going to translate these coordinates for me so that I don't need to worry about it. This is going to be literally it. We're just going to define a function called transcoord. And we're just going to literally just create a map, a dictionary of all of these values. So we have A is going to be equal to 0. And I'm just going to copy and paste the rest of this solution, because I cannot be bothered to type that all up. And then essentially what we do here is we're going to give it a, we're going to be giving it a tuple C. So then after, we're just going to return a tuple as well. And we're going to return the int C at 1 minus 1. So the rows start at, the columns start, are numbered 1, 2, 3, 4, 5, 6, 7, 8, 9. But then our list indexes are going to be starting at 0, right? So we're going to subtract 1 for that. And then after, we're going to also map the letter to the row number. So in this case, we're just going to access, right, in this dictionary, we're going to find the letter here, and then we're just going to return a number. So this is not necessary if you want to use a dictionary. But when I did this, I wanted to use a 2D list, so that's what I did. And the next thing that we want to think about is how we're actually going to approach this solution. Now, because what we're looking for is we're looking to find values that are dependent on others, right? And that to me really sounds like a recursion problem. So we keep going down and down and down until we hit the base case, which is having a defined value. So we're going to use a recursion in this way. You can use it with a loop, but it's a little less intuitive. But we're going to call our method here, our function here, compute value, and we're going to take the coordinate. And now remember how it says that it can't have a circular dependency, right? So what we're going to do is we're going to keep a set of all of the nodes that we've previously visited. So if we are going to a node that we previously visited, we now know it's a circular dependency. And then we know to just return star. So what we're doing is coordinate is going to be the current coordinate, right? Like A2 or B3 or whatever. And then BL is a blacklist essentially. It's a set of all of the coordinates that we've already been to. So in this case, when we're traversing this quote unquote graph, we do not want to hit a node that we've already been to. So the first thing we're going to do is we're just going to break up the coordinate into two variables just so it's a little easier on us. And then we're going to say if the current coordinate is in the blacklist, we're going to just return star. So if it says we've already been here before, we're just not going to go there. Next thing what we're going to do is we're going to check if it's a number, right? So if it's a number, we don't really need to do anything. So that's going to be our base. That's going to be another one of our base cases. So we can say if this number, now this is just a quick way to check if it's a number or not. We're going to go ahead and say we're going to store a spreadsheet at this at SS, and we're going to add the spreadsheet YX. We're going to create the spreadsheet later, but we already know it's going to be a 2D list. So at here, and if it's less than or equal to 9. So this will just check if it's a number. And if it is, then we can just go ahead and say, just return it. Now, if it isn't a number, there's also a possibility that it could be a star, right? So what we can do is we can say if is equal to a star, then we can also go ahead and return a star. And then finally, if it's not, that probably implies that we have a whole bunch of columns, right? We can go ahead and this is when our recursion starts. Now, do note that this question is simply saying or. So it's either or. It's either it either has a number or it has a whole bunch of coordinates. There isn't a mixing, so you can't do like A1 plus 2 or something. So what we can do here is we can say, so we're gonna first we're gonna store the sum, right? So we're adding stuff up, so we're gonna store this as a sum, and we're also going to store all of the wanted coordinates. So I'm just gonna call this Q, and we're gonna split it by the pluses. Then we're going to loop through all the cells in the queue. Now we're going to be creating the blacklist set, and we're going to be adding the current coordinate, right? Because we don't want to loop back on this current coordinate. And then now let's go ahead and translate these coordinates now. So what we're doing here is we might already have a blacklist, right? We might already be working with a blacklist. So what BL.union with H is it merges the two blacklists together, so that as we go down, our blacklist can actually get longer. So now this is the result. So this is the result. So we're now computing the value for every single cell that is inside this current cell. So that's where our recursion kicks in now. So now we can say, well, if R doesn't equal star, we can go ahead and add it to the sum. Otherwise, if any one of these values is I don't know why this got all off. If any one of the values is undefined, our whole value is undefined, right? So what we can just, what is going on with this? Okay, well, regardless. Right, any single one of those like any single one of our dependencies has a star, that means we can't figure out the value of our current cell either, right? Because that value is undefined. So the value of our whole cell is also undefined. And then once we've looped through all the cells that are inside our cell, we'll simply return the sum. So if it hasn't gotten a star, that means that these must all have been numbers. So we are adding to the sum every single time, right? So then after we'll have we'll have the sum right here. That is our compute value function. Does that make sense to everyone? So first, again, I'm just going to go over this. We first check if the coordinate is inside an already visited list, right? So if we've already gone there, that means it's going to be a recursive dependency. So we are going to return a star. Next, you want to check if the number is already defined. So if it's a number, we're just going to directly return what we already have. If it's not a number, we want to check if it's star. So a star means that it has an undefined value. So we're just going to return a star again. Otherwise, if it's not a star and it's not a number, that means that there are cell coordinates, right? So now we need to compute the value of all those coordinates. So what we can do now is we can say, okay, so let's set up a sum because they're all sums. We will then find out all the coordinates that we need. And then we're going to iterate through every single one of those dependencies and trying to find the value of that, right? So first we're going to create a new set, which is going to be our additional blacklist. We're going to add the current coordinate we're at. And then we're going to compute the value of the dependency, right? So first we're going to translate the coordinates from our letters to just numbers. And then we're going to merge the two blacklists, right? Because remember that this is a recursive function. So we might already have nodes that we aren't allowed to visit, right? From like higher up. So we're going to merge our two blacklists together and then pass this all to the compute value function. And now if the value that we get is a star, it isn't a star, that means it's a number, then we can add it to our sum. Otherwise, if even one of those cells is a star, that means we can't figure out the value at all, right? So then we can just directly return a star. So if that hasn't happened by the end of this loop, that means that we've probably successfully found a sum. So we can just directly return the sum. So next, we're actually going to set up the question. So the very first thing we're going to do is going to create a spreadsheet. Right, so this is easy. We're just going to input.split, and it gives us 10 rows. So there we go. That's our spreadsheet. And now it asks us so now we need to process the spreadsheet. So we are just going to iterate through every single cell. Remember that when you have a 2D list, right, it's not x comma y as a regular coordinate is, it's y comma x, right? So we're just going to be iterating through it that way. It doesn't really matter in this case. And now we're just going to say, and this is our initial blacklist here. It's empty, right? Because we're at the beginning. Okay, and now we just need to print it out again. In this case, we're just going to use, we're just going to iterate through every single column here. So every single row here. And we're going to print. So this is probably a new function. You haven't seen this. This is .join. So we'll demonstrate what this does. So let's say that I have a list of letters. Okay, we're going to call this, right? When I run .join, let's say I use a star here. What this does is in between every single one of these elements, it adds this string here. So I can say like that. And then between, oh, that's a terrible example because you can't actually tell. Right, but like for example, this, it adds those bars across all of after every single element here, except for the last one. So we can use the same thing for our list, right? So we're gonna have a list of values, like whatever, right? And then after we can simply by running .join here, we can actually create a spreadsheet again. So that's just how we can display it. And that is our solution here. Just kidding. Because this will work a bit. Oh boy. Oh no, this is fine. Okay, no, I thought this is an error relating to something else. Okay, we're good. Phew. Okay. So if we just take the sample input here. it runs, right? And we get the correct answer, which is fine. Okay, so these test cases are actually straight from the CMC website. So these are the test cases that they actually used to test all of the programs. So we can take this, and we'll see that we'll run into a problem quite quickly. S3. Let's say this one. So this is our test data here. You can see there's a lot of dependencies, right? A lot of things depending on each other. So if we try to put this into here, we might notice a small little issue. Yep, it's taken forever, right? That's way over the 1 second limit you have. Now, to anyone who paid attention last week, this might sound very similar to what we did with Fibonacci, right? When we had those gigantic numbers that had so many dependencies, our code essentially ground to a halt. And that's what's happening here. So if we remember what we did here last time, we needed to memoize. So we needed to store, because, right, like for example, if I'm referring to J4, let's just find something. J4, look, I'm referring to J4 1 time, 2 time, 3 times, 4. I'm referring to J4 so many times, right? Why recalculate the value of J4 when I can just store the value? It's not going to change, right? So that's what we need to do. We want to implement some sort of memory so that we avoid that. The easiest way to do this is to actually just edit the spreadsheet. So the first thing that we should do is, I believe all we need to do though, is to do this. We can just say we have this R value here, right, for the coordinate here. So what we can do here is we can just edit the spreadsheet directly and just say, okay, well, where are we going? We're going here. And that we're just going to set it equal to R. That should work. There we go. All right, so by editing the spreadsheet directly, you save a lot more on memory. But if you're going directly from last week's solution to this week's, you might not run against it immediately. But I figured that it's probably just easier and more straightforward if I just directly edit the spreadsheet for you guys. But just if you did implement it using a memory, like a secondary memory 2D list, that's also fine. You have quite a decent amount of memory this time. So you wouldn't have been penalized too much. But definitely for bigger solutions, you definitely want to already use existing data structures instead of creating new. So in case you're wondering how you wanted to, if you wanted to implement it as a memory 2D list, what you would do is you would just initialize a memory thing here. Just say, right, make it empty, because again, Python doesn't. You can't just allocate list size. You need to actually fill it with stuff. So in this case, we're going to fill it with nothing. And then what you can do here is you can just say, okay, before I even do anything, if memory at y at x doesn't equal none, so there's something there, we can just return mem at y at x. And then when we do this, instead of doing ss, we'll just do mem. Okay, so that's if you want to do it as a memory, but the more memory efficient and slightly cleaner approach is to just directly edit the spreadsheet. So I'm assuming most of you guys right now, you do a bit of planning, right? When you're looking at a problem, you kind of assess what you need, and what the constraints are, but you don't really think too much about how your actual algorithm is designed. Maybe if you have a TLE or an MLE, you'll try to optimize it a bit, but normally you just kind of go with the flow and play it by ear. And that's fine so far. But as problems get a little more complex, it's really important that you spend a little bit of time thinking about how your algorithm is actually designed and how it works. So we're going to be transitioning into a phase where we're going to be exploring some popular algorithm designs and how we can adapt our problems or adapt our solutions, to kind of fit those and the advantages of different designs. So some popular algorithm designs, first of all, is brute force. You probably are quite familiar with this one. It's super fast. and easy to create. And for simple problems, it gets the job done, right? But once the solution kind of goes really complex, or the problem's very complex, your time and memory efficiency just nosedives, and your solution will probably be very unreadable. And right, there'll be probably a lot of edge cases that you're handling, and a lot of confusing code. But for now, it's probably okay, right? It gets the job done, and it's pretty simple to implement. The next type of algorithm is called divide and conquer. So divide and conquer algorithms break down the problems into many small parts until they're able to be solved directly. And then after, the program just takes all of those simple solutions and kind of does the exact opposite. And then after, it does the exact opposite, combines all of those simple solutions to get your final solution. So this can really increase efficiency. And if you have a multi-core CPU, right, you're always thinking like 4 cores, 6 cores, 8 cores, you can take advantage of that and have multiple cores working on different things. Because right now, all our code is kind of dependent on an earlier version of the code, right? So like, for example, if I have like S equals 2, then I have S plus 2, and then S equals S plus 2, and then S equals S plus 5, you need to wait for the result of S plus 2 before you can do this next instruction, right? But with divide and conquer, we just split up the task so that it's a self-contained package, and any core, it doesn't need any additional information to be able to solve the problem. It can return it, and then it will just get combined later. Now, next up is something called a greedy algorithm. So a greedy algorithm tries to make the optimal choice at each step in the hopes of finding the overall optimal way to solve a problem, right? So for example, let's say that you are outside, right? And you're lost in the jungle. A greedy algorithm would take every single path, like every fork in the road independently, and say, okay, which one right now in this situation is the best? So, right, if you see a big pond, you'll probably go to the pond, right? If you see a lot of, a clearing or something, you'll probably go there, right? But that kind of ignores the fact that sometimes a less optimal path will lead you to an incredibly optimal path, right? So let's say there was like a super swampy, disgusting place, but then right after there's a road. If you're using a greedy algorithm, you won't find that road because it's hidden behind it, like a suboptimal solution at the time, right? Like if you had between like a muddy swamp and like a clean pond, well, you'd probably go to the pond, right? And that's kind of the downside of a greedy algorithm, is you run the risk of missing very optimal choices that are hidden between suboptimal ones. Now, the final type of algorithm design that we're going to be looking at before the CCC is dynamic programming. Dynamic programming solves a problem by splitting it into many overlapping subproblems. So that's very similar to what we did with Fibonacci, right? Where every branch, once you start branching out, you start getting the same answers, right? You need the same parts, right? Like for example, if you're finding 2, right? You'll need the third Fibonacci, if you're finding the 5th Fibonacci number. So if you're finding the 5th Fibonacci number, you'll need, right, the third Fibonacci number multiple times, right? First, you're going to need it to find the 5th one, right? You need to do 4 plus 3. And then the 4th one also needs 3 plus 2, right? So you're doing it twice. So there's an overlapping subproblem. So what dynamic programming does is it'll solve that problem once and then store the value of it later. So that's an example of that is recursion with memoization. So we've already kind of touched on dynamic programming. Now, why is that important? Well, because Dijkstra is a greedy algorithm. So I wanted to introduce you guys to what exactly a greedy algorithm is. So Dijkstra's algorithm is an algorithm to find the shortest path between nodes in a weighted graph with only non-negative weights. All right. So your weights need to be either 0 or positive. Now, it was conceived by Edgar W. Doofenshmirtz in 1956, and it's commonly used to create basic navigation systems or network routing systems. Now, if you guys are fans of any TV shows, you know that Doofenshmirtz is not a real last name, at least. His actual name was Edgar W. Dijkstra. I guess nobody got the reference, which is fine. Okay, well, whatever. So Dijkstra was created by Edgar W. Dijkstra in 1956. And as a greedy algorithm, it chooses the path with the lowest weight at every junction, keeping track of the currently known shortest distance from each node to the start node. And if it finds a shorter path, it'll just update that path. So kind of it takes into consideration a little more than just blindly going in and saying yes, no, yes, no, yes, no. Now this process will continue until the shortest path to find every node between the start and destination is found, and then that will result in you getting the shortest path from the start to the end. All right, so that might have not made sense, but you'll kind of get what that means. So similar to BFS and DFS, Dijkstra has kind of its hallmark data structure, and that is a priority queue. So it's very similar in nature to a queue, but in addition to storing the upcoming nodes, it also attaches a priority to them. So elements with a higher priority, so this not necessarily is the highest order number, usually it's actually the lowest number. They have a higher priority that are served first. They're served first. So an example of a priority queue in real life would be like a hospital triage system, right? Where patients who are in most critical condition are in the front of the line. Right? Like the person having the stomach flu is probably going to get pushed back by the person who, has multiple gunshot wounds or whatever, right? So that's the same thing here. And what we store in that priority, is the weight, the weight of everything of that node, of getting to that node. So not only the weight of that node, but also all preceding nodes. So let's go on and implement this. Next up, we are going to look at the graph. So this is going to be the graph that we're going to be using. Very similar to past graphs. However, I've added weights to all of the edges and just added a few more edges just so that, there's actually a purpose of making this program and you can't just easily trace the shortest path. So let's get started. We have an adjacency list, so this is very similar, but this time, instead of just storing the adjacent node here, we are going to also store the weight, right? So I'm going to just do the first node, first couple ones, and then I'll just copy and paste the rest. So for node 0 here, we are connected to node 1, and it has a weight of 2. For another node 0, it's also connected to 4. That has a weight of 3. And it's also connected to 2, and that has a weight of 5. Now moving on to node 1, it's connected to 0, right? This is an undirected graph, right? So they're reciprocal. It's also connected to 4 with a weight of 1. And it's connected to 3 with a weight of 9. Okay, so does that make sense? So instead of just storing the edge here, we have the node. We also have the weight of that edge. This is our graph here. Now just take a look at this. I'm going to give it just a minute just to take a look. Next up, we're going to import queue. But not any type of queue. We're going to be importing priority queue. Right? We need the priority queue. Now you can use a list to make a priority queue, but it's a lot more work. It's already pre-made, so you might as well use it. In this case, this priority queue, the lower the number, the higher the priority. Next, we're going to create a list here to store all of the distances, right? Because remember, Dijkstra compares the current shortest distance with the next possible shortest distance. And if it's smaller, it'll actually update that distance to what it is. So here we have 8 nodes here. So we're just going to give I in range 8. Now, if you're just finding one node, right, you just need, you can just use a single variable and just call it, shortest or whatever, and set it to like some large number, right? So we want it to be extremely large, for like a million, a billion, or whatever. It needs to be higher than the highest possible cost that you could have. Yeah, you can use infinity, whatever. I like doing funny things, like I might just randomly put something. It doesn't really matter as long as it's bigger than the most expensive path possible. You're fine. In this case, we set it to 1,000,000, right? Because if we don't set it to 1,000,000, right, Dijkstra is, if it's like set to 0 or whatever, when Dijkstra's comparing, it's going to say, oh, well, this one's obviously more than 0, so I'm just going to skip over, and you're actually never going to get an actual, where is my, there we go. You're actually never going to get, the algorithm working, right? So it needs to be larger so that it'll actually check and it won't just skip over it. So next, let's actually initialize the queue. And we're going to say the start node is 0. We're going to add it again, same thing, but this time our priority, right? So the distance from start to start is 0. So we're adding that, and then we're putting start. And we're going to just update that now as well. Now this is going to look very similar to BFS now. We're just going to iterate and say cur is equal to q.get. And our current node number is that. And now we're just going to look in the possible nodes. So this is just a quick intermediate step here. You can also just do this if you want. But it's good for debugging purposes. So we can say for p impossible, we're going to fetch the weight of that edge and also get the next node. All right. And now what we're going to do here is, this is the kind of the crucial part. We're going to say if the distance of this node, remember, this distance is not just the weight of the node, but it's actually the shortest weight to get to the node from the start. So this is the node's weight plus everything before it, right? So keep that in mind. And adding, so if the distance to the current node plus the proposed weight is less than the distance that we currently have, right? Now you can see why we want that 1,000,000, right? Otherwise, this will always fail. It will always be false. If we can find, if this path right here is shorter than the current one we have, well, let's go ahead and go to it, right? So we'll say next node is now equal to the weight of this path. And then we're just going to queue it up again. Right. And now this should work. Right. So now if we print out dist here, we'll see that we get these lists, and we can actually verify this. If we go to the graph we use. So it says that the distance between 0 and 0 is 0. Okay, I think we can all agree with that. Distance from 0 to 1 is 2. That is the shortest one. Distance from 0 to 2 is 5. That's also shortest. Distance from 0 to 3 is 5. So, sorry, is 4. So we go 3 plus 1 is 4 here. Distance to 4 is 3. That makes sense. Distance to 5 is 7. So that makes sense here. It goes this way. All right, now distance to 6 is also 7. Now this one might not look obvious at the beginning, but you can see it can go 2 plus 1 plus 1 plus 2 plus 1. So that is 3 plus 4. That's 7. And then after 2, 7 is 6. So it's just the exact same one, except we don't need to add another 1 there. So as you can see, we traversed the graph successfully and we found the shortest path.